So how fast is the car going when it sees the accident? So at this point right here, it's going 100 kilometers an hour. And how far away is the accident? 80. It's just like bang. It is 80 what? Meters. It's 80 meters. It's a really long slowdown otherwise. Okay. So there's the accident, 80 meters. Got it. Now it says what constant deceleration, at least what constant deceleration is needed so that you don't hit the accident. Meaning basically it's asking what's the minimum deceleration? What's the minimum deceleration? So essentially, we'll translate it again. It's asking what's the deceleration so the car, if it had a constant deceleration, will stop in exactly 80 meters. Will stop in exactly 80 meters. That's essentially what it's asking. What's the first issue you notice about what I've drawn is correct, but what's the first thing we have to take care of? Or what should we take care of first? Units. This is huge. This is by far, if you look at all of the proper methodology, the most common mistake inside people's work who do the proper thing is they mess up right here. They'll carry it down and they'll get an answer that's off by a factor of like 100 or 10,000 because they haven't taken care of this. You either need to be in kilometers or meters. Which ones do you want to go to? I like going to meters. Either one functionally is about the same difficulty level. Why do I prefer going to meters?
Because we have a better idea.
I don't like decimals, right? If you go to kilometers, you have to start using decimals. You have to avoid using decimals. I would rather use slightly larger numbers than go to decimal land, personally. So let's just change this, for example. So instead of 100 kilometers an hour, what is it going to be? 100,000 meters per hour. Now, that's not a traditional velocity. It's not a traditional velocity, but do we have our units unified? Yeah, they are. Okay, so first of all, what is this question asking? To answer this question, you would need to have a sentence something like, I would need a constant what? We're looking for a constant deceleration. So we're looking for an acceleration. Deceleration just means the answer better be negative. But are we going to label it negative to begin with? No. So we know the acceleration at time t is going to be what? Some constant. Let's go with this. If the acceleration at time t is some constant, what's the velocity going to be? Constant times t plus some other constant. Exactly. What did we just do? We just anti-differentiated. We anti-differentiated this. Why do you have to add the constant?
Because we don't know if it was there or not.
Exactly. You don't know where it was. When you take the derivative of velocity, if there's a constant that's along for the ride, what happens to the constant?
It goes away.
It goes away. Great. So if that's the velocity, what's the position function going to be? C over 2 t plus some other constant, right? You can use, sometimes people like using C1, C2, and C3. I like doing this, especially since we're really limited to 3 variables here. Well, 3 unknowns. What else do we know? What is the velocity at time 0? No.
Oh, no.
100,000 kilometers, not oh, that's really, really fast. Meters per hour. Oh, it's actually meters, not just per hour, right? We're not dealing with acceleration. Meters per hour. Okay. You can. You could if you want. That's fine. That's fine. This is something I'm going to set too. The perspective is going to be important here. I'm going to give you the one that I think is the easiest to use. How far has the car traveled at time 0? S of 0 is going to be 0. You can invert this. You can say he's at 80 here at time 0, right? And then he's at 0 here. You can do it that way. I think it's a lot more logical to do it this way. Okay, so do we know how much time passes before he stops?
No.
No. So what's the velocity at time stop?
0.
Yeah, he better have stopped, right? What's the position at time stop? 80. 80. He's stopping in exactly 80 meters. He's stopping in exactly 80 meters. So if he stops in exactly 80 meters, this will give us the minimum deceleration needed to stop in 80 meters.
I thought the crash is at 80 meters.
It is, yeah, I know. You're like, if you go through a tunnel that's 10 meters wide and you have a truck that's 10 meters wide, what happens? I understand what your conundrum here. What we're getting is the boundary here. So this will tell us, this constraint will tell us the minimum deceleration needed to stop in exactly 80 meters. So yes, to avoid the car, we'll need to have a slightly better or slightly larger deceleration. Does that make sense?
Yeah.
We now have enough information to solve for, what are we eventually trying to solve for?
C.
Our target is C. So let's set up some simultaneous equations. Let's use this first one right here. The velocity at 0 is 100,000. So we know that 100,000 is going to be equal to what? C times 0 plus what?
D.
Plus D. So what's D equal to? 100,000. So where can we plug that 100,000 into now? S of t. Plug in what you know immediately. You know that S of t is therefore C over 2 t squared plus 100,000 t plus e. Okay, so we've now used this right here. What about s of 0 is 0? That means when you plug in 0 for time into our s function, what do you get out of it? 0. So we now know, though, so we know that 0 is equal to 0 plus 0 plus e. So what does e have to be?
0.
E, therefore, must be 0. So now that we have e is 0, where do we plug that in? The s of t. So now we know that s of t is equal to c over 2 t squared plus dt. We now have this equation right there. There's our position function. We've used these two. We now have two more things to use. We have velocity at time stop, and we have position at time stop. Let's use both of them and see what happens. We're right here, so let's plug that in. So what do we now know? 80 is equal to c over 2 ts squared plus, and it's not d, what is it? Yeah, so what can we say that instead? What was the nice way of writing that? Yeah, let's write it as 10 to the 5th. Plus 10 to the 5th time stop. So there's 1. And what do we do with the other piece of information? Where do we plug that one into? Well, no, we have to plug now with the velocity. What I meant is the other equation, this one right here. So now we plug that in, and what do we end up with? 0 is equal to what? C times time stop plus 10 to the what? 10 to the 5th. So we have equation number 1 right here, and we have equation number 2 right there. How many unknowns do we have? We have C and what? TS. We have C and TS. How many equations do we have? 2. Solve for TS. Actually, I'll amend that. Do you actually care what TS is? Not really. You're using it as a means to end up getting what? C. So do this for me. Solve those for C right now. Solve those for C. The one from the test was something like this. G of x was equal to the integral from 0 to x squared of like 1 over the square root of 2 plus t to the 4th dt. And I asked you for what g prime of x is. Can someone tell me? Just raise your hand and tell me what g prime of x is. Yes.
1 over root 2 plus
T to the 8th.
Or x would be x.
Oh, is it x? Oh, it's x now, yeah. So it's x squared to the 4th, and then what's on the outside? Then what's on the outside?
2x. 2x.
Why?
Because the derivative of x squared.
Why? Why do you need that?
Because the chain rule is there.
Because of the chain rule. There it is, right there. All you're doing is you're throwing x squared in. Why is it? Why do we need this 2x? Well, there's usually a floating invisible what right there? 1. If this was just x, it would be 1 over 2 plus x to the 4th, not x squared to the 4th times 1. Usually you don't write that in because you don't need to. Okay, so what does this mean? What is g, boys and girls? G is the integral from 0 to x of f of t dt, and this is f of t. So if you go from, if you're integrating from 0 to 0, how far have you gone?
Nowhere.
So what's the area under the curve of something that has no base?
0.
Nothing. It is 0, correct. What about from 0 to 1?
1.5.
It's 1/2, correct, because you're going from here to here. It's this area. That's a triangle. What about from 0 to 2?
0.
It's going to go back to 0 because this is net change. It's going to be positive above and negative below. And then, Will, what's 3? Will. 他是 Will.
Negative half.
Negative 1/2. What's 4? Colin?
Oh, 4 is 0 again, but you put 1/2.
Yeah.
2. Oh, I put it in the wrong place. Yeah, so I skipped. It should be what? 0?
0.
Negative 1/2. And then what? What's 0 is 4? Yeah. And what's 5 going to be? What's 6 going to be? 4, right? And then what happens if I asked you for g of 7? You'd have to kind of what?
Yes.
You'd have to guess. I mean, you'd know you're going to add on more than 1/2, right? More than 1/2. So this is the integral from 0 to 7. So g of 7, you know g of 7 would be greater than 4 plus 1/2. Do you see why?
Yeah.
Because it's 4 all the way up
It's
to
not a
2,
straight
6.
line.
It's concave down, so it's going to be above the straight line from there to there, or judging by that picture. Oh, that was B. Okay, so you think it's going to be what? Around what? Like, I don't know, 5.6. Sure. It's going to be, no, that would be incorrect. You know, it's going to be greater. It's going to be greater, but that would be a decent estimate. That would be fine. It would be nice if there was more detail, but that's okay. Where does G have a maximum value? Where do you think G on this graph has a maximum value?
6.
You sure?
Or no.
G is the area under the curve. So where is the area under the curve
7.
greatest?
7.
7. It's as long as you're above the x-axis, you're adding to it, correct? You're adding to it. So it's positive, then it's negative, but then it grows. It's still growing, right? It's not asking where G is. It's not asking where f of t is greatest. Where is f of t greatest?
6.
6. But where's g of x greatest? 7. 7. So how do you sketch a rough graph? What do you do to sketch a rough graph?
In a minimum.
You just plot the points you just found. Exactly. So at 0, it's here. And then at 1, it's a half. And then at 2, it's 0. And at 3, it's what? Negative 1/2. And then 4, it's 0. 5, it's 1/2. 6, it's what? 4. So this actually is going to look like, it's going to look like that. And then it's going to slow down a little bit. What is g of 7? If this is 4, you know, it's up here somewhere, right? It slows down a little bit. Like that. Does that make sense?
Yeah.
Yeah. Okay, good.